Okay, so we've been looking at taking given data, possibly in the form of x and y coordinates, maybe in some other form, and finding a polynomial model that best fits that data so that we can use it to make predictions about the data or work with the data in some other way. One of the ways to do this that we've been talking about is using what we call finite differences. When we use finite differences, we're talking about the differences in y coordinates as we progress from point to point. Now, in order to do that, you must have constant change in x. Okay, so your x coordinates as you go from one to the next must be changing the same amount each time in steady increments. So we can see in this problem we have from going -6 to -3, that would be adding 3. From -3 to 0, that would be adding 3. From 0 to 3 would be adding 3. 3 to 6 would be adding 3. And 6 to 9 would also be adding 3. So because we have a constant increment of increase in x every time, we're going to be able to use what we call finite differences. We'll look at some cases here in a moment where we don't have that situation and what we can do. But anyway, let's quick review. We'll go through how to do finite differences, and we'll look at this specific problem so we can identify what degree polynomial best fits this. We'll start off with the first differences. The first differences are going to be gotten from the original data, 16 minus -9. That would be 25. 26 minus 16 is 10. In each case, all I'm doing is subtracting the y coordinates from one point to the next. From 41 to 26, that would be a difference of, 15. 71 minus 40, or 78, 78 minus 41 would be 37. And 151 minus 78 is going to be 73. So we can see that our first differences are there, and what we're looking for is the same value to be repeated there. And in this case, we do not have any of the first differences being the same. So if that's the case, what we're going to do is go look at our second differences. And I'll abbreviate that there real quick. Second differences are going to be between these values. 10 minus 25, that's -15. 15 minus 10, that's +5. 37 minus 15 would be 22, and 73 minus 37 is, 36. So, again, we don't see the same numbers here, so we know that we do not have a second degree polynomial to fit this. It's not the best thing. So, let's look at the third differences and see if that maybe fits. Again, we'll just look at the numbers that we have in the second differences and compare those. So from 5 to -15, that is a difference of 20. 22 to 5 is a difference of 17. 36 minus 22 would be a difference of, 14. So again, we don't see the same values, so we are pretty certain that we don't have a third degree polynomial here. So we'll check the fourth differences, and I think you can see, and a lot of people start asking what's going to happen if we run out. Well, hopefully we don't do that. 17 minus 20 would be -3, and 14 minus 17 is -3. So this is something we get excited about. So that means that we have a fourth degree polynomial that's going to fit this data, or it is quartic in nature. We've talked about second degree would be quadratic, first degree, of course, is linear, third degree would be cubic, and a fourth degree polynomial, which we have in this case, would be quartic. So now what we're going to do is we're going to find what polynomial would best fit that. So we're going to go to our calculator, and I'm just going to pause here for a second. Okay, and now I've brought the calculator up here on the screen, and just so what we would do now is we would go and press the stat key. Now the stat key is just to the left of the arrow up here at the top. So we push that stat key, and you can see it's red there. We're going to select Edit from the menu so that we can enter our data into the list. Now I've taken a moment here, and I'll just clear this one out to avoid any confusion for you. I've taken a moment here already, and I've entered this data from the list. And if you go back and look at our original data, you can see our x values, -6, -3, 0, 3, 6, 9. I've got those in list 1. And our y values, I need to correct that. That's not -9, 16. It should be just -9. So let me enter that real quickly. -9, 16, 26, 41, 78, and 151 were the y values. I've put those in list 2. Now, if you go back and remember, we just said that we had a quartic polynomial was going to fit this data best. So we're going to use that information and just tell the calculator that that's what we want to do, is make a quartic equation. So we're going to quit this, and we will press the stat key again. And this time we will go over to the calc menu. Now if you look at the calc menu, you'll see the options down here around 6 and 7 and 5 and basically 4, 5, 6, and 7. We have the different options for a cubic regression, which would be a third-degree polynomial, a quadratic regression, which would be second degree, linear regression for first degree, and quartic regression, which is what we're going to use here in this case because we have a fourth degree polynomial. We've already determined by finite differences that was best. So we'll enter this data, and or we'll tell the calculator to use this pattern, and we're going to tell it that our data has already been entered. We entered it in list 1 for our x coordinates. We'll put a comma here separating that, and then we used list 2 for our y coordinates, and we want to tell the calculator, after it figures out what equation is going to fit best, to go ahead and put that equation in y1, which would be in the y equals list. So we push vars, we go over to y vars and press function y1. And that's telling the calculator again to take the x coordinates from list 1, the y coordinates from list 2, make an equation that fits that data, and put it in y1. So we do that, and you can see I have lots of data here, but it tells me the basic form up at the top of the screen, and or at the top of the calculator screen, y equals ax to the fourth, bx to the third, plus so on and so on. Well, the a represents your coefficient of the quartic term. The b is the coefficient of your cubic term, and so on. So this would tell us real quickly that our equation would be y equals, and I'm just going to estimate here, -0.0015 x to the fourth plus 0.11419 or 1142 x to the third, 0.2917 x to the second plus 3.1389 x to the first plus 26. That would be your quartic polynomial that would represent this data to the best of its ability. It might not be perfect, but in this case I think it is. If we look at y equals, you can see it's already got that there. Now I'm not going to scroll all the way over, but it's put that equation in the calculator for us, so we can use it, and we're going to make some use of these later on, so it's good to get in the habit of putting them there. But that's how we regress a set of data to fit a polynomial equation. Let's look at a couple more examples. I want to show you. We're going to look at this example here where we're going to look at an application. We have a vehicle that we're going to look at its gas consumption based on the speed that it's being driven. And as we all know about cars, the faster you drive them, sometimes you burn a little bit more fuel. Also, different speeds burn different levels of fuel, and we want to look at this to maybe see what the optimal speed is, which is going to burn the least amount of gas. So we want to find what would fit this situation best, what level polynomial, what degree. So we're going to look at our first differences. Again, we have a steady incremental change of 5 in our x-coordinates, the speed. So we'll look at our gas as the y-coordinate, and we'll look at the differences between that. So we'll say 25 minus 23.8, that's 1.2. 25.2 minus 25 is 0.2. 25 minus 25.2 would be negative 0.2. 25.4 minus 25 would be 0.4. 27 minus 25.4 would be 1.6. 30.6 minus 27 is 3.6. And 37 minus 30.6 would be 6.4. So those are the first differences for this equation or this set of data, and we can see that we do not have any constant differences. So we're going to go to the second differences, and we'll look at 0.2 minus 1.2. That's negative 1. Negative 0.2 minus 0.2 would be negative 0.4. 0.4 minus negative 0.2 would be 0.6. 1.6 minus 0.4 would be 1.2. 3.6 minus 1.6 would be 2. And 6.4 minus 3.6 is 2.8. And again, this gets a little tedious, but we're just really subtracting each case to see where we get the same numbers. We don't have that in the second differences, so let's check the third. Negative 0.4 minus negative 1 would be 0.6. 0.6 minus negative 0.4 would be 1. 1.2 minus 0.6 is 0.6. 2 minus 1.2 is 0.8, and 2.8 minus 2 is 0.8. Now, I want to bring this situation up because up to this point, all of the examples we looked at have had it work out perfectly. And in this case, we do not see the differences coming out to be exactly the same. However, we do see the numbers are very close to being the same. In fact, we have some repetitions. We have 0.6 there twice, and we have 0.8 there twice. 0.6 and 0.8 are also both very close in nature. So this is going to be sufficient for us to use. We'll sacrifice a little bit of accuracy here, understanding that nothing is going to always work out perfect. So we will use the third differences in this case and say that we have a third degree polynomial. So this is the best fit. We're not necessarily going to come up with something that's going to fit perfectly, but again, this is the best fit that we can come up with. So we're going to take this over to the calculator and look at it, and I'll try to go ahead and enter that data for you. Now, going back to the calculator, we're going to pick up by entering the data. Now, in the interest of time, we'll push stat, edit, and in the interest of time, again, I've already entered this data for us. So we would just type that list of speeds into our X list, or list 1, 25, 30, 35, 40, and so on. And then we will type the gas consumption that was used for each respective speed limit or speed in list 2. And we'll consider those our y coordinates. Now, as we said earlier, we had a cubic equation because we found that the third differences, while they weren't perfectly the same, they were very close to being similar. So we're going to say that we have a cubic regression is what we want, and we're going to go press stat, and we're going to calculate, and we will select the cubic regression, which is option 6 in that list. So we'll go down to cubic regression, we'll press enter, and again we want to tell it to use the data that we have in list 1. And we want to use that with the data in list 2 as our y coordinates. L1 would be our x coordinates. And we want to store that in y1. Now, you might have a different version of operating system on your calculator, and it might ask a little bit differently how you want that inputted. But this one is actually more complicated. The other version actually says, what do you want your x list to be? That would be L1. What do you want your y list to be? That would be L2. And where do you want to store the regression equation? And that would be y1. So you're just going to basically enter this same stuff in to that format as well. So don't stress out if it doesn't look exactly like what my screen looks like. If it does, you just do the same thing, of course. We do the cubic regression here, and we can find that our equation is going to be 0.001 x to the third minus 0.113 x to the second plus 4.1339 or 4.1434, excuse me, x minus 24.87. And that equation has been stored in the calculator in Y1. So if we were going to take this and use it, we could actually use that to predict the amount of gas consumption at different speeds. And I'll show you how to do that here in just a second. Okay, so we look at this, and the equation that we said fits the data is y equals, or f of x equals 0.001x to the third minus 0.113x squared plus 4.134x minus 24.867. So suppose we had that equation and we wanted to predict the amount of gas consumption this vehicle would use, or this vehicle would have, if it was going 52 miles per hour. Well, basically, all we would need to do to find that would be to plug 52 in for x into this equation. So I'll give you a second to plug 52 in for x and see what that does, and see if you can actually get the prediction here. Okay, we continue, and you can see hopefully that you were able to consume 28.15 gallons of gas traveling at 52 miles per hour. Now, I'm assuming you probably did this in the long form of doing this. Going back to the calculator, we had that equation stored in Y1. So you can actually tell the calculator to do this calculation for you. Now again, we were going 52 miles per hour. So if we wanted to get the calculator to plug 52 into that equation, we're just going to tell the calculator, hey, take that equation, Y1, and I want you to take that equation Y1 and plug the number 52 into it. And basically we just tell it, we put 52 in parentheses next to it, and that tells the calculator to plug that value in, and we get 28.15 gallons of gas, which is what we said in the on the screen previously. So that's how you would make that calculation. Okay, well, let's look at this example. The table below shows the number of high school graduates in a particular state for each of the given years. Use a polynomial model to estimate the number of graduates that were in the year 1999. Notice that the year 1999 is not here. So we're going to want to find how many graduates were in that year. Well, if we look real quickly at our x values, which would be the years in this case, we can see that we do not have a good situation. Meaning that this is a 2-year jump, this is a 4-year jump. And if you remember what we said earlier, we have to have a constant incremental change in our x coordinates. So we don't have that situation here, so we cannot use finite differences. So what we have to do is resort to a different method. And what we're going to do is go to our calculator, and we're going to calculate something we call R squared. Now, in doing this, finding R squared, we're going to find the R squared value for our linear regression, our quadratic regression, our cubic regression, and our quartic regression. Now, R squared, I won't go all into detail, but it basically gives us it's a numerical value that gives us a measurement of how closely the regression equation that we come up with fits the data that we have. If R squared is close to 1, we want to get a value for R squared that is close to 1 as we can. Now, it'll range, it's a decimal usually, and the higher that decimal gets and the closer it gets to 1 or -1, the better it fits our situation. So what we're going to do is we're going to find the linear R squared and the quadratic R squared and the cubic R squared and quartic as well, and we'll discover which one is better at fitting the actual data that we have. So we want to check this out, and to do this we're going to have to use a calculator. Now we pretty much know how to get R squared, or something we've already been doing. Some of you may already see it on your calculator. To make sure that your calculator is set up to give you this, all you need to do is go to the catalog feature, which is second 0, and that pulls up a catalog of all the available functions for the calculator. You're going to want to scroll down to the D section, and you can press the alpha D key to get that to happen faster. And you'll see a selection of diagnostic on and diagnostic off. And in order to get R squared to be a value that the calculator will show you, you want to turn diagnostic on. So we'll go to diagnostic on from this menu, and we'll press enter, and we press it again, and it'll say done. Now when it says done, basically the calculator is saying, okay, I'm going to give you all the diagnostics on different things as we work with the data you've given me. So we're going to go now and check the R squared for these regressions. The first we'll do is the linear regression. So we'll go to Stat Calc, and we will select linear regression. Selecting that from the list, we will tell it to use the data. I'm sorry, I skipped ahead. Let me tell you, I've already entered my data. I should have told you that. I entered the data, and I want to bring up one important point here now, and I've got a little ahead of myself. The problem that we're looking at deals with years, and years are not a specific, they don't have a numerical value really. They're what we call interval measures, and it's not really what we would call consider a specific numerical value. So what we do anytime we have years or some time period as a x coordinate, we start off with the first one being a value of 0, and then we go from there. So to go from 1989 to 1991, that was an increase of 2. So going from 0, that would make 1991 2. And 1995 then would be however far 1995 is from 1989, we would go that far from 0. So that would be 6. From 1989 to 1996 would be 7. From 1999 to 1998 would be 9. And then from 1989 to the year 2000 would be 11. So we're going to count those as our x-coordinates instead of actually typing in the years. Again, the numerical value of the years really doesn't make any sense to the problem. So we start off with 0 being our first year, and we go from there. So I've entered those values in for our x-coordinates, and I've entered our y-coordinates being the number of graduates that happen in each one of those years. And again, the year 0 stands for 1989, the year 2 stands for 1991, and so on. So again, we'll look at the linear regression now. Going back to where I was, so we'll select number 4 from the list, and that will do the linear regression. We're going to do the linear regression with list 1 and list 2, and we want to store it in y1, although it's not necessarily that important to store this one. We'll keep it there just in case. If we look at this, you can see that the R squared value is 0.3176. So I'm going to go ahead and record that on my list, and 0.3176, and that'll be something we can look at in a minute. Now let's continue by looking at the quadratic R squared, and let's see how that looks. Well, quadratic is option 5, which pick that, and we'll do the quadratic regression with list 1, comma, list 2, comma, y1. And when we do that, you can see that we have an R squared now of 0.481, and that would round off to be 94819. So let's list that off, 0.4189. Is that right? It was 4819, wasn't it? Okay, let me fix that real quickly. 4819. All right. Okay, now let's look at the cubic model. You can see that the quadratic model was a little bit better. It's closer to 1 than the linear model was, so it's probably a little bit better representation of the data. Let's see if we can find something a little bit better there. We look at the cubic model, and we'll go stat, calc, cubic, which is option 6, and we do the cubic regression for list 1, comma, list 2, comma, y1, and hopefully you're following along with me as I do this. And we see that R squared here is 0.6832 or thereabouts. So let's look at that and record that, 0.6832. Getting much better than our previous values, but still, let's see if we can get something better. So let's look at the quartic in this case and see what the R squared value is on that. So we go down and choose quartic, which is option 7, and do the quartic regression of list 1, list 2, y1, and hopefully you're getting to go as fast as I am now. I've done this so many times. And we do this regression, and you can see you actually have to scroll down. So we push the down arrow, and we can scroll down and see R squared, wow, is 0.99979. I mean, it's really, really close to, I'm just going to write it like that, 0.99999. Actually, it's even higher than that, though. So we can see that this is very close to being 1. So we want a value of 1 to fit our data, so that's good for us. So we can see that the quartic model in this case would be the best to use. So we can go back now and get our data from that to write the actual equation. Let's see, we have y would be equal to negative 10.027 x to the 4th. What was it? 027. And then we had 238.815 or 816 plus 238.816 x to the 3rd. And I'm going to run out of space, but minus 1750.66. Sorry, minus 1750.66. And I'm running out of space. Let's see if I can move this over. I'll try this. Yeah, that's the way it's always doing for me. There we go. Not too bad, but could be better. All right, and that would be x to the 2nd. And then we've got 3593.257. Wow, okay. Plus 3593.27x. And that was 257, wasn't it? Sorry. Okay, let's see how this is going to work. All right, 257x. And then we look at the last value, which is our constant term, would be 59336.47 plus 59336.47. Okay, so this long thing is our quartic equation. Now, thank goodness we don't have to do a lot of work with it, but it's very long. But what we can do is now plug the year 1999 into this and get a good estimate for the number of graduates that was in 1999. So let's go ahead and take that equation. Thank goodness we saved it in the calculator. It's right here. And we want to use that equation that's in Y1 and plug in the year 1999. Well, going back to the data, remember we used 0 to represent 1989. So 1999 would have a value of x equals 10. So what we want to do is we want to plug 10 into this equation. And if you remember what I said, we just push y1, we get y1 up on the screen, and we tell the calculator to plug 10 into it. And that'll give us a good estimate, 58,744.76. So we would have 58,744.76 grads in 1999. And of course, that's a prediction. It's not the actual number. Of course, you can't have 0.76 graduates, but that's a good prediction based on our polynomial model for the number of graduates in 1999. Okay, hopefully you've learned a little bit. Remember, again, we're going to use R squared in situations where we do not have incremental changes in our x coordinates. And we'll find the best R squared for our data by going through all the regressions and seeing which one fits best. Have a good day.